All right. Thank you, people. Thank you for joining us. I'm very happy to have with us Eleonora Giunchiglia. She's an assistant professor at Imperial College. She got her PhD from Oxford with Thomas Lukasiewicz, and she also did a postdoc at TU in Vienna. And I know Eleonora and her work since I was doing my postdoc, and I was admiring her work, trying to put constraints into neural networks and essentially try to enforce reliability in the way we expect the system to behave. And this is extremely important, I believe. So many of the things that we're going to talk about today, I think they're going to resonate with what we do in the lab, but also with many things that also I see people here are interested in. So Eleonora is also a big pillar in the community of neurosymbolic AI and integration. In fact, she's coming here for the Viva of Laurent, you're now the doctor, so congratulations also. And you're coming here almost from California, where you had like a neurosymbolic conference and you were program chair of that. So without further ado, please, stage is yours.
Thank you so much. Well, thank you very much, Antonio, for your extremely kind word as usual. And thank you so much, everybody, for coming. As Antonio said, I've been studying the problem of how to make reliable deep learning systems, whatever reliable means. We will see later what it means. And before I delve into the topics, obviously I want to thank all my collaborators. The works that I will show today are not just the result of my own work, it's also the result of their sweat and tears. So yeah, thanks also to them. And yeah, well, I always say, I think now everybody agrees with this slide. I'm a bit of an engineer by training, so I always like to start by what is the problem. And the problem is that, as we all know, deep learning models are great, establishing state-of-the-art results in many different domains, but sometimes they make some mistakes that anybody defining an intelligent being would never commit. And so these mistakes are actually so bad at times that they make the news, right? And so we have these titles from the New York Times saying to kill the driverless Tesla car crash. And this is a problem for us because it hinders the trust that the users have in this mechanism. So if you have come to any of my talk, I always say that I started with this big question: how can we solve this problem? Then years in academia have made me a bit more humble. So now I say, how can we at least alleviate this problem? And if we look at the machine learning pipeline from a holistic perspective, it kind of looks like this. So if you have trained any machine learning model, what you have done is you've taken a data set, you have created a model, you have trained it, you have tested it, and finally you have deployed it. Now, as I said, I'm an engineer, so first thing I did at the very beginning of my PhD, so very long time ago at this point, I started comparing this pipeline with what are the standard software engineering pipelines, right? So here I put literally the software engineering pipelines from standard books. So you have the waterfall, the agile. Okay, this is the spiral, a bit more complex, used in bigger organizations. But what was striking for me was the fact that if you look at all the software engineering pipelines, they always start from the requirements definition, right? And what even us as professors, we teach to our own students is don't even think writing a line of code if you don't know what the requirements of your problem are, right? And then meanwhile, you look at what we do with machine learning problems, we give a data set to our students and we are like, let's hope for the best, right? So there is a clear mismatch. And this is kind of fine if you think of machine learning as statistics. So you have a data set and you say, oh, I want to fit some loss function. But now these machine learning models have become so powerful that they are starting to be systems that act in the world and their actions have real consequences, right? So we can no longer think of machine learning models as statistical models. We need to start thinking of them as systems that act in the real world and hence need the requirements satisfaction, okay? So obviously, I wasn't the first one to think about this. Already back in the days, there were people trying to solve this problem. And namely in 2017, back then, there were two major lines of research going on. The first one was, let's start from a very easy one, the testing techniques. So there was this entire line of research that would say, okay, you know what, we have a bunch of properties that we want our models to satisfy. The easiest way we can find to find a bug is come up with testing. So like essentially we try to find a way to generate synthetic data that cover all the possible data points in our distributions, and we try to test our model in corner cases, right? And then there are verification techniques. So if for those of you that come from the verification community, this means that essentially you create an abstraction of your model, so a simpler version of your model, and then you pass this to, for example, an SMT solver. So for example, you have a neural network, you rectify all the functions or the nonlinear functions, and then you can pass this to an SMT solver. Again, what is the problem though with these models? Well, there are, in my opinion, there were two main limitations. The first one is that if you find a bug with both of these, then you're sure there is a bug. But if you don't find a bug, then it's not, at least back in the day, now there are verification techniques that can give you this. But if you don't find a bug, then you're not sure whether there is not a bug. And then secondly, which was the thing that bugged me the most, was the fact that, as you can see, this happens very late into the pipeline, right? So at this point, you have already created one model, trained it, and only at testing time is when you worry about requirements. So people like me and Antonio and the neurosymbolic AI community, what we try to do is push, thinking about requirements a bit earlier into the pipeline. And so what I try to do still, and what we try to do is two things, having two goals at the same time. First of all, we try to build models that by design are compliant with our constraints or requirements. And secondly, we want them to learn from the requirements themselves. And why I put both of these questions here? Well, this is very important for me, because if you listen to a lot of debates in safe AI, you hear a lot of arguments that say you need to have a compromise between safety and performance, right? Well, personal opinion, I strongly disagree with that. Why? Because requirements are background knowledge. And if you think about it, the neural networks that work are not the fit-for neural network where everything is connected to everything else, but they are the ones where we have injected our inductive biases, right? So CNNs work because we know that images are rotation and translation invariant, right? So what if we have a way to take any sort of requirements, sort of compile them in layers, and then have an automatic way to inject inductive biases into the network, okay? So if there is one very simple point to take away from today is, maybe it's not so true that we need to have a compromise between safety and performance. We can actually be smarter about it. At least that's my opinion. Okay, now the question is, okay, you have told us all of this, it's all fluff. How can you actually do this? And I always start with this very simple example. Suppose you have two classes, A and B, and you have a very simple requirement or constraint that says A implies B. Well, what this means is that whenever you are predicting the class A, you should also predict the class B, okay? And also suppose that our data set has this shape. So a data point is red if it doesn't belong to a class, and it's blue if it belongs to the class. So for example, this data point doesn't belong to either class A or class B, while this data point belongs to the class B, but not to the class A. As you can see, our data set is actually compliant with our background knowledge, right? Because all the data points that belong to the class A also belong to the class B, okay? How would we solve this with a standard neural network? Neural network with two inputs, two outputs, standard binary cross entropy loss. And if you actually implement it with a very tiny neural network, just 7 neurons, I'm a big fan of synthetic data sets, this is what you get. So as you can see, well, two things. If you take a very tiny neural network, it struggles to learn even such a simple shape. And also, if you look at these tiny corners, you can see that there exists some area for which the class A is predicted and class B is not. So the more red the area is, you have a color map here, the more the neural network is confident that the data point doesn't belong to the class, and the more blue, so here it's super confident it belongs to the class B. Okay, so can we do better? Because as you can see here, we haven't used at all our knowledge. We have just said we learn from the data. So what is the intuition? Well, the intuition is that the requirements define what we call the safe output space of the model, okay? And so if you want to plot the current output space of the model, it will look something like this. You have that we can output anything between 0 and 1 from both A and B. And if you just look at the propositional logic constraint, it's simply telling you, you cannot predict A at 1 and B at 0. So you are excluding one point in the entire space. However, neural networks don't work really in the discrete domain. They work in the continuous, right? So how can we relax this definition that is given in the discrete domain to the continuous? Well, at least for us, if you talk about probabilistic logic, then it's a bit different. But for us, what we want to have is that the output for the class B is always greater or equal than the output for the class A, right? What does this guarantee? Well, if you are given a threshold, any sort of threshold, this guarantees that whenever you're predicting A, you're also predicting B. And how can you do this? Well, if you take this, I say, geometric way of thinking, it's incredibly easy, because all you have to do is say, oh, look, I keep A as it is, and then I rewrite B as the maximum between A and B. Now, by definition, the final output is guaranteed to be compliant with A implies B. And also, the network is now aware that A is a sufficient condition to also conclude B, right? So if you put A as 0.8, B will be 0.8 by definition. And also, coincidentally, I don't know if you're familiar with the Gödel-T norm, with the fuzzy logic. If you think about it, the maximum is just rewriting B as A or B, right? And it's true that if you know that A implies B, writing B or writing A or B is completely equivalent. Now, is this enough to make it work? Well, yes, but one has to pay attention. So one question that I got a lot was, why didn't people do it before you, right? It's such a simple solution. And the reason why it didn't work was because, I don't know if, well, people didn't look at the gradients. So in order to make this work, we had to look at the gradients of what was happening during training. So let's have a look at what happens in our loss function, at the gradients in our loss function, when we have the ground truth for A equal to 0, the ground truth for B equal to 1. So we are looking at those two terms of the loss function. And also we have that the output for the class A is greater than the output for the class B. In this case, what happens is that our output for the class A and for the class B are the same, right? And now, if we go and substitute, I would have thought something in the tiny corner didn't matter, but if we go and substitute the value for the output A into our loss function, we see that essentially we're telling the neural network to both increase and decrease the output for the class A. And obviously this can cause problems, right? Can we fix it? Well, yes, thankfully. Okay. What we have to do is simply make the layer behave a bit differently during training, kind of like dropout. You have two different behaviors on the ground, whether you're using it for training or for inference. So let's have a look. We don't change anything for the loss for the function for a class A. We change something for the class B. Let's break it down. Nothing changes when the ground truth for B is 0. And we only change it when the ground truth for B is 1. And what we do is simply multiplying the output for A times its own ground truth, which means that when the ground truth for A is 0, this goes to 0, right? That's about it. So we cannot have the gradients going in the wrong direction. So now, if we do the substitutions, you get these gradients and everything goes in the right direction. So if you do this, and this, we will see it's all automated, it's simply masking in our layer, you can take the same neural network, and these are the decision boundaries you get. Now, an obvious question is, how is it possible, right? Because you haven't changed at all the number of ways you have in your neural network. So you haven't changed really the expressive power of the neural network. How is it possible that with the same network, you just get these decision boundaries? Well, to answer this question, we need to have a look at what happens here. right before the layer. So what are the values of HA and HB, okay? If we plot those decision boundaries, this is what we get. So as you can see, the output for the class A, well, it's what it is, it remains the same. But for B, the network is learning that A is a sufficient condition to conclude B. So it can simply output 0 over here, and then we say it delegates the prediction to A, right? And obviously, this is a much easier shape to learn, right? Because it is a convex function. So it's just learning something like this, which is much easier to learn than something like this. And then you simply compose it, right? Now, another question one can ask is, okay, but sometimes it's convenient to decompose problems, but sometimes it's not, right? So suppose we have now this situation. If we have this situation, if you want to decompose B as B set minus A and A, then you would need to learn a donut, right? Because you would need to learn this crown over here. Again, more complex function because it's, again, non-convex. But if we look at what happens before the layer, this is what's happening. And why is this case? Well, because with the maximum, we are not telling the neural network you have to decompose the problem. We are saying, we are simply telling it A is a sufficient condition to conclude B, then do whatever you want. And the networks, as you know, they are lazy objects, so they tend to learn whatever function is easier. So this is in the very simple case. Everything works. Now, what happens if we have more complex requirements? What happens if we have propositional logic requirements? Well, let's start with something easier. Suppose we still have a rule, so something with a body and the head, and now it looks something like this. So this is telling us, if we have predicted the labels A1 to AK, but not the labels AK plus 1 to AN, then you need to predict the label A. What is this rule telling us? Well, it's just a generalization of what we have seen before. This rule is simply defining a lower bound for the label for the class A, right? And what is this lower bound? Well, it's nothing else than the minimum between all the outputs for the classes A1 to AK and 1 minus the negated atom, okay? Notice again, if you are familiar with the T-norms and fuzzy logic, this is equivalent to the golden T-norm of the body, okay? Okay, so if we have one requirement with, as a rule, with positive head, we know what to do. If we have negative head, what can we do? Well, it's very simple. If you have a negative head, this now defines an upper bound on your label, right? Which is simply 1 minus and the same equation for the body, okay? So now we know how to deal with set of hierarchical constraints, single requirement with positive head, single requirement with negative head. But propositional logic looks something like this. You have ors and ands and nots and so on and so forth. What can you do? Well, again, I like examples. So suppose you have a neural network with 4 outputs, blue, green, yellow, and red. And suppose that your requirements are given in a CNF form, so in conjunctive normal form. And you have given 3 clauses. Full, it's a positive literal, and empty is a negative literal. So this you read as green or not blue or red, no blue or no green or yellow, and so on and so forth. And you have a set of clauses, okay? Question, we don't know how to deal with clauses, right? So what can we do? Well, the first thing we need to do is defining an ordering. This essentially tells us the order of computation of our labels. So this is telling us, if we pick blue first, blue can do whatever it wants. Then we decide the value, the bounds for green on the ground of blue. Then we are deciding the bounds of yellow on the ground of blue and green. And then what do we do? Well, first we need to understand how to compile, right, this layer, this clauses into a layer. So we traverse the order backwards. So we start from the bottom and we start from red, okay? We take red and we say, okay, we first transform these 2 clauses into rules, following the rule that not A or B is equivalent to A implies B, okay? So we have 2 rules now. Now, you might notice that if we apply both the rules at the same time, we might end up in a bit of a pickle, because now we have red and not red implied at the same time. So we cannot have these rules activated at the same time, right? So what do we need to do? We need to ensure that not both of the rules are activated at the same time, which entails doing resolutions between the two of them. So if you do resolution between the two of these two, you get no green and blue implies yellow. For those of you that are not familiar with the resolution, essentially this is equivalent to take the body of one of the rules, let's say with positive head, and negate one of the atoms in the body of the other, right? This essentially disables the other rule, right? So you make sure that you cannot have a rule with a positive head and a rule with a negative head activated at the same time. Then you move on and you start this cycle again. You translate the clause into a rule, which is the one on top. And then you say, does there exist a couple of clauses, one where yellow appears positively and one in which it appears negatively? And I'll do resolution. And I go on. Then I took care of this. When I look at green, nothing happens. And when I look at blue, nothing happens. So why did we do this process? Well, because if you think about it, when you decide, like, we want to have a layer that is doing a series of operations and it is defining bounds, right? And the layer, by definition, needs to be acyclic, right? So we want to make sure that once we fix the value for one label, we don't have to go back because we arrive to the end and we realize, oh, actually, my constraints are unsatisfiable if I fit this value to false. So I need to make sure that every step, there always exists a solution for all the next steps, okay? So now we have our rules. We know what to do with them. So now we have our rules, and we start traversing the ordering in the right direction. So we go from blue to green to yellow. We start from blue, and we look at the heads, and we're like, is there a rule with blue in the head? No. So the lower bound is 0, the upper bound is 1. We go to green. Is there a rule where green appears in the head? No. Lower bound to 0, upper bound to 1. Yellow, haha, yellow gets more interesting. So as you can see, there are no rules where yellow appears negatively in the head, so upper bound is 1. But we have two rules where the yellow appears positively in the head, and so we take the highest of the two bounds, right? And so we take the maximum. And indeed, this is nothing else than the maximum between the body of this rule and the body of this rule, right? And then if we consider red, we have two rules, one with positive head and one with negative head. And so we have one upper bound and one lower bound, okay? So now we know the upper bound and lower bound for every label, right? What can we do with them? Well, it's very easy. You can think of it as you have an upper bound, a single upper bound, a single lower bound, and then if the value is anywhere over here, you're just putting the value equal to the lower bound if it's lower and equal to the upper bound if it's higher. So you're just mapping back, you're projecting back to the bounds. And this can be done with this very simple operation that can be done very easily with PyTorch. So as you can see, everything was done with max, min, 1 minus. All operations that are super easy to implement in PyTorch. And this is just to give you an overview of the entire system. So we started with our requirements, which are given in CNF. We have defined an ordering, which is user-defined, can be random, we don't care. We transformed our clauses into rules, and our procedures guarantees also that we are doing the minimum number of resolution steps given the ordering. We can forget about saturated rules, which give us a bit tighter bounds. Then what we do is we build a dependency graph, which essentially tells us, okay, if two labels don't depend on each other, we can compute their value in parallel. And why do we do this? Because GPUs are very good at parallel operations, but they are very bad at sequentials. So what we want to do is to parallelize as much as possible, right? So we build a dependency graph, we assign each label to different levels, and then we build a layer for every level as we saw. And this essentially allows us to build layers that are not very tall, very short, quite fat, to be honest, but that's fine because GPUs are very happy to do things in parallel. So the idea is that to have a number of sequential steps that is sort of bounded by the number of variables, and then allow the layer to grow a lot in width. And what can we do with this? Well, we applied this method to the radar dataset, which is this autonomous driving dataset, where essentially we have a bunch of videos, and each video is annotated with bounding boxes about all the relevant agents in the scene. So for example, and each bounding box is annotated with agent in the bounding box, the set of actions, and the set of locations. So you can have here a pedestrian that is moving away on the left pavement. You have a traffic light that is green. Traffic lights, for example, are not given a position, or a bus that is moving towards you in the incoming lane, and so on and so forth. And then we have annotated this with hundreds of requirements, which essentially tell you things like, for each bounding box, there needs to be at least an agent. A traffic light cannot be red and green at the same time. You know, pedestrians ought to have hazard lights flashing, things like this. And then obviously the first thing we tried was actually testing whether standard deep learning models violate these requirements. And just to give you a qualitative example, these are a prediction that we got with one of the state-of-the-art models back then. I can guarantee you there are a huge amount of violations. And as you can imagine, this is not great, neither from the point of accuracy, but also from the point of safety, because what do you do with a prediction that tells you traffic light red and green? And what we have done then is take exactly the same 3D retina net, apply the requirements layer on top, and just qualitatively, these are the very cute prediction that we can make. Okay, this is qualitative, though. I promise you that we also improve the performance. So this is the actual performance for more quantitative analysis. So this is how the frame in average precision, which is the standard metric used for this task for action detection. And the red line is how it grows for the standard 3D retina net model. And all the lines above represent our model with the requirements layer with different orderings. Because as you can imagine, orderings have an impact on the performance. Now, ironically, the line I'm most proud of is the pink one, which is the lowest, because that was obtained with a random ordering. So it means that even if you pick a random ordering, you still get something that improves a bit the performance. Then you can obviously be a bit smarter about it. So, for example, the blue line, or the green line actually, is an ordering that is based on frequency. So as you can imagine, this layer, since you have a sequential computation, right, of the labels, you have also a problem of propagation of the errors, right? And so the basic intuition one can have is you can put easy labels at the beginning and then complex labels at the end. And one simple heuristic to decide whether a label is easy or not to learn is whether it's an imbalanced label or not. The more balanced it is, the earlier we put it in the ordering, and the more imbalanced it was, the later we put it in the ordering. And with that, we got, I don't know, 2.5% improvement. As I say, it's not like great improvements, but it is an improvement and you get something that is safe. So why not? It's a win-win. Okay, so if we are still with me, yes, and I have the time, can we extend this and go beyond propositional logic and ask ourselves, what if every atom is now a linear inequality? So what if now we have a set of clauses like this, phi1 or phi2 or phi n, and every phi is now a linear inequality like this. And we want essentially to generalize the procedure followed in CCM+, okay? Which was the method I presented earlier. So why is this cool? Well, this is quite cool because both with propositional logic and with set of linear inequalities, well, you can model like convex spaces or like polytopes, like one of these. But now suddenly, if you have disjunctions over linear inequalities, you can model not only non-convex spaces, but even disconnected ones, right? So one could like draw very cute pictures like this and say, oh, we can model this type of spaces. And what is the basic intuition? Well, This was actually a work that was done in 2 steps. So we started first with just a set of linear inequalities, and then we extended with disjunctions of linear inequalities. But basically, the basic idea is that now we have that each linear inequality is defined naturally, either a lower or an upper bound, right? What are the problems? That a set of disjunctions of linear inequalities define multiple bounds, right? We no longer have one upper bound, one lower bound, we have multiple. And the question is, we don't know how to do resolution or reduction now. We need to generalize this resolution step, right? So as usual, we start with a very simple case. So we start with a single variable and a single clause. So if we have a single variable and a single clause, you have just variables and constant. And so it means that you always have a single left bound and a single right bound. Worst case scenario, you overlap and essentially have no bounds, but at maximum you have one left bound and one right bound, right? This is good. In this case, 5 and 10. If we have a set of clauses, right? Again, in a single variable, now you can have multiple bounds, right? And essentially you have the safe output space is a bunch of intervals, you can think of it, right? You have a set of intervals, but if you have a data point, so if the neural network is giving you a data point, an output, then you will have a single closest satisfying left bound and a single closest satisfying right bound, right? So because if you have a set of intervals, you can either be in the safe output space or you can be in between them, right? Something like this. So what can you do? Well, in this case, you can write this very, I don't know, big equation, which simply tells you, okay, if I am here in an interval, I want to map to the closest between the left and the right bound. And if I am in the interval, I stay where I am, which amounts to this. Okay, very easy. And this can be done very easily on PyTorch. These are 3 functions, so not a problem. Problem, we don't know how to do resolution, right? That was the problem. We don't know how to deal now, how to go from multiple to a single variable to multiple variables. And to generalize what we have seen, we need to generalize the resolution step. So comes to play cut-in planes resolution, which is our generalization of a resolution step, which looks something like this. But the basic idea, if I show you with an example, is incredibly easy, is that you take a clause where, let's say, x5 appears positively. You take a clause where x5 appears negatively, and then you reduce all the pairs, all of these pairs, right? So for example, here, you reduce between x5 major than x1 and x5 inferior or equal than x2, right? And you get x1 inferior or equal than x2, or x5 major or equal than x3, okay? So this is a generalization of a resolution step, which allows us, in practice, to generalize what we've done in the propositional logic case. So let's have a look at what happens in practice, but it's very similar. If we are given, let's say, 3 constraints like this, what we can do is we define an ordering over our variables exactly in the same way. Then what do? We traverse the ordering again in the opposite direction. So we start from x5. We look at the constraints where x5 appears, and then we start to do our resolution step. So first, we do exactly the resolution step that I showed you before, right? So we reduce between x5 major or equal than x1 and x5 inferior or equal than x2. And this, as you can imagine, it tells us either x1 is inferior than x2, which gives us this interval, or it's major than x3, right? This resolution step, as you can see, essentially ensures us that there exists at least one of these intervals, and that is not empty, right? Then what do? Well, now we have to do the resolution step between these two, because x5 still appears there. and it gives us x1 inferior or equal than x4. Again, it ensures us that there exists at least an interval, right? That is not empty. And then, differently from what we had before, we have to do also resolution between something we have obtained, because now x5 can appear both positively and negatively in a clause, with x5 inferior or equal than x4, right? And this gives us this equation, which again ensures us that there is always a non-empty interval. So we can now forget about x5. We are left with these two. We look at x4. The good thing is that x4, appears negatively in both the constraints, so we don't have to do any resolution. We can just forget about them, because obviously if they're both negative, they just overlap and we will have simply two intervals that look like this. Then we can forget about them and we go on x3, x2, x1. We are good. So these are our constraints, like what we have to work with. And what do we do with these? Well, now we start traversing, right, from the other side. So the final value for x1 is equal to x1 itself. The final value for x2 is equal to x2. The final value for x3 is equal to x3. x4, what do we have to do? Well, we say, okay, x4 actually needs to be major or equal than the final value of x1. And if this is satisfied, then we are good. Otherwise, x4 needs to be major or equal than the final value of x3. So if this is true, as you can see, we can have that x1 is inferior than x3 and it's good. Otherwise, we would need to put x3 over here, and this interval wouldn't exist. And then we do the same for x5, right? Now we know the value for x4, and so we substitute and we get our bounds. So as you can see, this is the more complex case, but again, it's just telling us, okay, if this is true, then we have these two intervals, and then we can go back to our problem of mapping to the closest bound. And that's it. We are done. Because at every step, we have gone back to the single variable case. So this is the entire idea. The idea behind this work so far has been, we compile a layer. The layer essentially ensures us that we can fix the value of our variable. And by fixing it, we are ensuring that there is a solution for all the next steps. And that's it. What can you do with it? Well, in this case, we applied it to the data generation case. In this case, for example, we had 109 features collected from the ICU. And the task is to, given this data set, to create a new synthetic one that has the same distribution as the original one, but none of the original data points. Why is this useful? Well, because now with GDPR, with privacy, a lot of companies have a lot of data, but they don't want to share them. So they want to generate synthetic data sets on which they can train their model. What is the problem? That we are facing a lot of them, but these data points make no sense. Why? Because neural networks are very good at understanding correlations between features, but not very able to understand crisp boundaries, right? So in this data set, we had 31 requirements, but a simple one is that, as you can expect, the maximum hemoglobin that you record throughout the patient's stay should be always greater or equal than the minimum hemoglobin that you record, right? And indeed, if you plot the real data distribution, you get something like this. There are no data points in the red area, right? But if we take table gun, which was one of the state-of-the-art models, then you get something like this. So as you can see, as expected, neural networks, once again, great at understanding that there is this correlation between these two features, but they're not great with these boundaries. So you end up with a lot of data points that fall into the red area. Now, what we have done is we have added our layer as usual on in between the generator and the discriminator. And this is the data points that you get. Once again, just to give you an idea, not only you get something that is compliant by design with the requirements, but again, we get better performance, right? I mean, just visually, the distributions are much more similar, right? So with this, I close my talk. There are some open questions I have. I've so far, as you can see also from my talk, I've always proceeded in a way where I always try to extend the syntax of my constraints. So for example, right now we cannot support polynomials, we cannot support differential equations. So, you know, there is a world to explore over there. We would like to also apply some of the intuitions to autoregressive problems, which again opens to a new whole world of linear temporal logic and so temporal constraints. And finally, how can we drop the fully supervised assumption? Because as you can see, in all my tasks so far, either I was in the generative case or I was in a fully supervised case. And when you are in the, well, partially supervised case, you have problems like reasoning shortcuts. To be honest, we have a new paper coming at NeurIPS 2025 on how to mitigate these reasoning shortcuts, and it's coming soon out, promise. So that's all from me. Thank you very much for listening.